Greetings. In this lecture, we're going to look at a family of oxoacids, and then at the end, we'll have a look at the Lewis acid-base model. Before we begin, let's be sure we understand some very important concepts. A strong acid is one that has a weakly held hydrogen. And because that hydrogen is so weakly held, we typically find a strong acid without its hydrogen attached. On the other hand, weak acids are acids that have their hydrogens held onto very strongly. And for this reason, we typically find weak acids with their hydrogens attached. Very important idea to keep track of as we look at the following collection of oxoacids. This family of oxoacids is important because it will demonstrate how other factors, other than bond length and bond polarity, can affect the strength of an acid. And we'll begin with hypochlorous acid. Hypochlorous acid is a monoprotic acid with a single ionizable hydrogen that happens to be attached to an oxygen atom and to a chlorine atom, just like that. This is hypochlorous acid. Related to hypochlorous acid is chlorous acid, also a monoprotic acid attached to an oxygen, just as was the case for hypochlorous, attached to a chlorine. However, in the case of chlorous acid, we have an additional piece. We have another oxygen attached via a double bond to the chlorine. Now, we haven't in the past seen chlorine in this situation before. However, chlorine does have available d orbitals, and these available d orbitals permit it to bond more than once. In other words, chlorine can accommodate an expanded octet. Moving on to chloric acid. Chloric acid is also monoprotic. It has a single ionizable hydrogen attached to an oxygen, attached to a chlorine, attached to a doubly bonded oxygen, but just to make things interesting, there is yet another doubly bonded oxygen attached. Chlorine in this case is actually in the midst of 5 bonds, and this trend continues as we look at perchloric acid, a monoprotic acid again. Everything else is the same. An oxygen, a chlorine, a doubly bonded oxygen, another doubly bonded oxygen, and yet another doubly bonded oxygen. And so we have a total of 7 bonds in this case. Now, this is obviously a very logical progression, and it's something that we hope to understand in terms of acid strength. I've taken the liberty to include some other information, the K sub A values that you see on screen, and you should recall that on the left-hand side, as we look through this spectrum of numbers, we have the smallest K sub A value, 2.9 times 10 to the minus 8. On the other hand, on the far right, we have the largest K sub A value, which is infinity. Now, these K sub A values also tell me something about acid strength. A small K sub A value tells me that I have a weak, and in this case, of these 4 that I'm considering, the weakest acid. And on the far right-hand side, why the largest K sub A value tells me I have the strongest acid. Taking this one step further and remembering how we defined strong acids and weak acids above, we know that based upon these numbers, the weakest acid should have the most strongly held hydrogen. Let me say that in the following way. We can say that in this case, the case of hypochlorous acid, the HO bond is the strongest bond of these that we will consider, and that for perchloric acid, the HO bond is actually the weakest bond because that hydrogen falls off so easily and gives us this infinity K sub A value. So what we need to do is we need to understand why this bond right here is so strong, giving rise to weak base behavior, and why this bond is so weak, giving rise to strong acid behavior. And so we have a weak bond on the right and a strong bond on the left, and we would presume correctly that the chlorous acid and chloric acid that fall between these two extremes follow the same sort of pattern, and indeed they do. So the idea here is that in order for us to have a strong bond, let me sketch this out for you here. A strong bond positions electrons, or keeps electrons in the bond. Doesn't that make sense? If you want a bond to be strong, why, you need the electrons to stay in the bond. On the other hand, if the bond has been weakened, then it's because, in this case anyway, because bond lengths and electronegativities all being the same for all four possibilities, then a weak bond is weak because the electrons have somehow been removed from the bond. It's a little bit like taking the glue out of a glue joint. If the glue's not there, it's going to be weak. If the electrons are there, why, it'll be strong. So, here's what's going on. In the case of hypochlorous acid, on the left-hand side, there can be no doubt that the oxygen and the chlorine are both quite electronegative, and consequently, being electronegative, the electrons in the bond that connects the hydrogen to the oxygen are moved out of the bond just a little bit. That's right, the electron density moves out of the OH bond toward the oxygen and toward the chlorine, giving the hydrogen a slight positive charge. This is a good thing because we like to see the positive charges appearing on hydrogens. After all, that's the charge they need to have when they're released in order for us to have an acid. Now, here's the difference. If we move on to chlorous acid, we have the same oxygen and chlorine pulling electrons out of the bond, but we also have an additional oxygen. I'll put an exclamation point right there because the oxygen is capable of acting remotely. It isn't directly attached to the hydrogen, but it is able to exert itself and its electronegativity in a way that pulls the electrons out of the bond more so than in the previous case. And so the electrons are moved more out of the bond, and consequently this bond winds up being a little bit weaker because the electrons aren't where they're supposed to be. Well, you can probably see what happens now. Now we have, in the case of chloric acid, we have electrons being pulled towards this oxygen, electrons being pulled towards this oxygen, both of them acting remotely, and consequently what happens, the electrons in the OH bond wind up shifting even more so. With a bigger arrow to suggest that. Consequently, what happens is the hydrogen winds up with an even bigger positive charge than it had previously. Take this up one last step to perchloric acid. In the case of perchloric acid, why, electrons are being attracted to this oxygen, electrons are being attracted to this oxygen, electrons are being attracted to the third oxygen, and in effect what happens is there is a large-scale movement of electrons out of the OH bond, weakening it and creating the weakest bond of the four that we've considered here so far. So, the reason for the difference in acidic behavior as we've looked through these oxo acids is not because of differing bond lengths. All of the OH bond lengths are the same. It's not really because of differences in local electronegativities. In all cases, we have an oxygen attached to a hydrogen, and if there are differences, there must be something else responsible. What is responsible is that in the case of these oxo acids, the addition of remote oxygens and the extra electronegativity that they bring to the molecule produces a drifting of the electrons out of the OH bond, creating a weaker bond and thus a stronger acid. Now, to finish up today, what we're going to do is have a quick look at a different acid-base model, something known as the Lewis acid-base model. What's interesting about the Lewis acid-base model is that it doesn't involve hydrogens at all. The Lewis acid-base model is actually the most general-purpose, all-around useful model for acid-base behavior that we have. It's very powerful because it applies to many situations that up to this point we might not have even considered acids and bases. Now, to help us with this, we'll need some definitions, and an acid from this point of view is something that can receive electrons. It is an electron pair receiver. A base, on the other hand, is something called an electron pair donor. Interesting that no mention is made whatsoever of hydrogens. Now, rest assured that the Lewis acid-base model, when applied to those things that we already recognize as acids and bases, either Lowry-Bronsted or Arrhenius, it'll work just fine there too. But the Lewis acid-base model applies to even greater numbers of situations. And should you go on to take a class in organic chemistry, why, you'll be using the Lewis acid-base model to describe a lot of what goes on from the organic chemist's point of view. But just to demonstrate this and give you an example to think about, what we're going to do is we're going to have a look at a substance known as boron trichloride. And as the name suggests, boron trichloride has a boron atom and 3 chlorines. The Lewis dot structure looks something like this. What's interesting about boron is that it's actually an exception to the octet rule. Boron is perfectly fine with 6 valence electrons, represented here by the 3 bonds, and then I'll give the chlorines their fair share of electron density, as they are not exceptions to the octet rule and require a total of 8. So there is a perfectly fair boron trichloride molecule. Now, what we're going to do is we're going to react boron trichloride with ammonia. And ammonia has a Lewis dot structure that looks something like this. It has hydrogens, which are exceptions to the octet rule. They follow their own duet rule, and we have 3 of them. And then nitrogen does have to have an octet, and it obtains its octet by keeping a lone pair on reserve. Now, when these 2 things react with one another, what we get is a species that looks something like this. We've still got the boron, and we still have it attached to the 3 chlorines that were there to begin with all of their lone pair, just like this. Okay? But here's what happens. The electron pair that the ammonia has as an extra winds up being involved as a shared bond that connects the boron to the nitrogen, which of course has its hydrogens attached as well. Okay? We could actually redraw this structure, and maybe I'll do that here. With the boron, try to give it a little more three-dimensional flair. The chlorines actually fold back a bit as a result of this. And there are still the chlorines there. And then we have the attachment to the nitrogen, and the hydrogens continue folded back as they would otherwise, just like this. And there's the final product. Now, what's interesting about this is that it's pretty clear, especially since I've used colors, black and red, to help with all of this, it's pretty clear that in creating the bond that connects the boron to the nitrogen, the electrons for that bond came from one species originally. Now, where did the electrons come from? They came from the nitrogen in ammonia. And according to our definition of Lewis acids and bases, anything that has a pair of electrons that it's going to donate is going to be referred to as the Lewis base. And so in this case, since the electrons that are going to be used to create that bond originated with the ammonia is known as the Lewis base. Well, that makes it pretty easy. You can actually see now what's got to be the Lewis acid. The Lewis acid is the species that is going to benefit from these electrons donated by the ammonium. Boron trichloride does have some space that it can use to accommodate these extra electrons. It does so and creates, and thus a bond is created connecting the boron to the nitrogen. To finish this off, I'm going to just describe this bond that forms. It is indeed a covalent bond. It is a covalent bond because the electrons are indeed shared. However, we're going to define it a little bit differently. We're going to define it as a coordinate covalent bond. And a coordinate covalent bond is a bond that is formed when the bond is formed as a result of electrons coming from one species only. And so in this case, it's a coordinate covalent bond because the 2 electrons came originally from one species. In this case, that species is the ammonia molecule. Okay? And so it's a coordinate covalent bond because the electrons were donated entirely by ammonia in this case, and it is an example of Lewis acid-base behavior because that which gives up, or that which contributes, I should say, an electron pair is what's known as the Lewis base, and that which is the lucky recipient of these extra electrons is known as the Lewis acid.